Okay, so I've been talking about what happens when we, in place of a Bode plot, in place of a Nyquist plot, where what do? We plot 1 plus GSHS on the S plane with essentially S traveling across a contour, which has ultimately boiled down to only the j omega part of the S being traversed along the imaginary axis. In between, I have often talked about this thing called Bode plot. So today I will introduce you a little bit to the basics of Bode plot. So a Bode plot is of a function. Fs will be maybe radians also, and this will be in decibels and sorry, this is generally in degrees. So we'll now look at how we can go about it. Let us say we choose a function so the first thing we can do is we can factorize this out. So this is step 1. Let's call this writing Fs in a suitable form. Then this is your first step. Second step, ensure that the so how do you do that? It's pretty easy. This one, these two are nice terms, so we don't have to do anything about this. So we have 100. Oh, sorry, there is a 10 out here. So from 100, but still I'll write it in the proper form. So I have to take 1 out here, and I'll be getting 1 plus s by 1 from the denominator. We take 10 out to get 1 plus s by 10 and 100 out. So if you should you have a quadratic factor, let us say 2. This should come out to be quadratic, p square. What is, yeah. So in this case, this will become this term is particularly important in case of a quadratic factor, as I will show later, because this essentially represents, when we write this as j omega, then this will become the omega square by what we will call as omega 0 square, where omega 0 will be a kind of a resonance frequency for this factor. So for this particular function, this will simplify into something like 0.1 So essentially we should be having a scalar part, then some linear factors both in numerator and denominator, also some quadratic factors. in numerator and denominator. We will see how to tackle each of these cases. So first, scalar or real or whatever. This is constant. This is pretty easy. If I have my Fs, which here substituting j omega for s will not make any difference. If this is my function, then what happens? And from here we use what decibels? That is about it. So what will our plots look like? So I'll just get a straight line. Here also I will simply get now one thing that you must remember, that this axis is And this kind of makes 20 has some historical basis. Why we use 20? I believe something to do with um, the gadgets, etc., for which purpose this decibel scale was first used, and um, because you can't have a zero, I mean 0 decibels will actually mean you actually have no number whose log is equal to 0. So we have instead 0 decibel, which corresponds to 20 log to the base 10 of a value 1. And this will be true for all the other plots as well. Next, we'll have a real pole. So if you have something like this, then this 10 is, its place is actually symbolically represented by omega 0. So Fj omega will be equal to this, you can write as so 20 log to the base 10 in decibels. So this form can be analyzed for a set of cases. Case 1, omega much less than omega 0. We call this, as a result, the low frequency part. That is, omega by omega 0 tends to 0. So what happens? To modulus fj omega in decibels, and this will come out as equal to approximately 0. Case 2. We call this the high frequency part. That is, omega by omega 0 in this case will be tending to infinity. In decibel will therefore be tending to we can kind of do a little simplification out here. We can do two things. One is we can get rid of this under root, and two, also get the whole thing on the top by expressing this as a power. It will be 1 plus something square to the power minus half. Sorry, this will be equal to, and there is a minus sign out here. And this can be approximated as
Sir, for the first one, omega by omega naught, sir, could we have just used the log series expansion and just kept it as omega by omega naught? I mean, 1 plus x, log of 1 plus x.
Good question. Let me draw the plot. Why you will understand that why, and then you will understand why we are not doing that. So 20 log 10, already it's been divided by 2, and this, when you approximate, it becomes 20 log 10 omega by omega 0 and if I take this 2 out, and this will actually be equal to and finally our case 3, we call this omega 0 as the break frequency, not resonance, mind you. And again, when I do the plot, you will understand why. So what does that become? Twenty log to the base 10, 1 plus 1 square under root, so 1 by root 2. Which will be 10 log to the base 10 of with a minus sign of 2. Now, since you people give your have given your pre-college examinations with calculators, and I use the log table, so I still know that log 2 is something like 0.293. Sorry, 0.3010. So this means this will ultimately boil down to minus 3 dB, and this 3 dB line you will find plays a big role in Bode plots of all kinds. So now we'll get into the business of plotting this whole thing on a Semilog graph sheet. So here we have this dB, and here we have this radians per second or hertz. And our expressions are tending to 0, we have 0, we have minus 20 log 10 or 20 log 10 omega 0 by omega. So again remember that what are these two? These are basically asymptotic representations of this log value. So first we have this zero dB line, and also this minus 3 dB line, which we can figure out pretty easily. And now we start drawing our plots. So from this side, we know that we can proceed this way as we start from small values of omega, and often we will also have to add to that, we'll also have that here also we are plotting in a log scale to cover a wide range of frequencies. So this approximation will become even better for us. So if we have that sort of a scenario, then what is the other data that we have? Somewhere out here I have my omega 0, and I do know that I have a point on my graph out here. What do I also know? That I have a line which will show up What is this line? If you consider that both the sides are in a log scale, then we have the graph will be so this will actually be a straight line on this plot, and if you plot this straight line, you will see that this is a line that at omega 0 at omega is equal to omega 0, this will be passing through this will be equal to zero. So omega is equal to omega 0, it has 0 dB. And what is its slope? It is 20 per what we call as decade. Decade meaning, if here we start with point say 0, 1 on a log graph. Are you familiar with the log graph paper? Well, on a log graph, actually we have the plots like this. 0.01, then this will be 0.1, then this will be a 1 somewhere, then 10, 10 square, so forth. They are equally spaced, and these gaps of 10 to the power, there is multiplication of 10, 0.1 to 1, these are known as a decade. So the slope is minus 20 dB per decade. So this will be a line which let me use a different pen. This will be a line like this. So we can now kind of approximate straight away by extending this line, and this line is already joined, and in our actual application we will kind of smoothen this line out. There are of course rules for that, to get the feel of the actual curve. Okay, so this is the reason why, as you had asked, that why I am not taking the first order term. It introduces unnecessary complications. We are getting a very good approximation by just following this simple rule. So how will the phase plot look like? So this will contribute 0, and this will come out, because it's in the denominator, this will come out as negative. So it will be 0 minus and you can use geometry to write this as tan inverse imaginary by real by 1. So it will come out as tan inverse omega by omega 0. Again, we consider 3 cases. Low frequency end, So this will be approximately equal to 0 degrees. High frequency and omega is equal to infinity. So tan inverse infinity, which is and a minus sign, so it will be minus 90 degrees. Omega is equal to omega 0 minus 45 degrees. So once again we have got three parts of the plot. And when we now draw this, on this side it will be in degrees. On this axis in a standard plot, this will be in but in a log scale. That means we'll be maybe starting with 0.1, but here it will be 0 degrees. This is a log scale. So this for our convenience will start with minus 180. Then we have a line maybe this is my 0 degrees line. So in between I'll have the minus 90 degrees out here, and here I'll have 45 degrees. So all that we know is at some place where let us say I have my omega 0, I have one point, and out here I have one line that is corresponding to omega is very low, and I'll also have another line corresponding to omega is very high. Unlike the magnitude part, we have a problem out here in that these are parallel lines, they don't intersect. So what is normally done is we choose arbitrarily to extend this up to a point corresponding to 0.1 omega 0 on this side and another point corresponding to 10 times omega 0. So we extend up to this, and then because of the nature of the plot, these two lines will be equidistant from this point, and then we join them together to get the approximate plot. The real plot actually looks more smoother. It is probably going to go a little beyond this and curve a little here and join like this. I think you will recall that you have seen similar plots when you have done your vibration course. So a very similar analysis will be there for a real zero, that is in this case, if you apply the same kind of idea, then you will get exactly the reverse of what you have got. This will be the 0 point. This is your Fj omega in decibels. This is log to the base 10 of omega, and this point will correspond to omega 0. This will have a slope of 20 decibels per decade. Decade meaning the per every the spacing between say 1 and 10, that is called a decade on this log axis. And likewise, when you are looking at the phase plot, you are going to see something that will look like this. But signs reversed. So this will correspond to your omega 0. These are approximations, remember. This is the low end part, this is the high end part, high frequency end part of the plot. I'm not going into details here, but if you look at these two sets of plots, now if you have a repeated pole, then what will happen? Give a little thought to that. In place of a slope of 20 dB per decade, it is going to get multiplied. If you have a square, then it will become, all that will happen is that if you go back further, then this, if it is a square term, then what is going to happen? There will be a 2 coming out already. So basically, in place of a 20 dB slope, rest of the stuff will remain the same, but you will have a 40 dB slope. That means this part will remain the same, but in place of having a minus 20 dB per decade slope, this will be 40 dB per decade slope. It will be a steeper slope. If you are looking out here, in place of 90 degrees, you will have a minus 180 degrees. And in place of this happening at 45, you will have this point omega 0 getting passed through at minus 90. So the same thing will happen when you have a 1 plus s by omega 0 square, or if you have a cube, just there will be straight away multiplication taking place. And here, before taking a break, I will just point out this to you, that one thing that you ought to realize if you give it a little bit of a thought is that apart from its other virtues, you have done at least a couple of plots, and if you take Nichols into account, 3 types of plots: root locus, you have Nyquist, you have Nichols. None of them actually, when you look at the plot, it gives you an intuitive idea of how your plants or systems transfer function could look like. This, however, gives you a clue that if you get an actual, you feed your plant a wide range of frequencies and obtain this plot that is doable, you can now, by doing superimposing your approximations on that experimentally obtained plot, you can kind of get an idea of how your system's transfer function looks like. You can get a reasonable approximation. So I'll take a break for 5 minutes, and then we will rejoin again, where we'll deal with this other part, that is how to deal with quadratic factors, before concluding this lecture.